In example 4.14, we're going to be looking at an algebraic approach to being able to prove that a function is either even, odd, or we can also prove that it's neither even nor odd. Now, from a geometric standpoint, the definition for even and odd tells us a little bit about what we might see from the graph. So if a function is even, then we know that it is supposed to show a y-axis symmetry. If a function is odd, then we know that it's going to show origin symmetry. But if you don't have the picture in front of you, and you don't want to actually go through the process of making the graph, then you need an algebraic approach to this. So that's what we're going to see here. For part A, we have f defined over all real numbers, and it's given by the equation f of x equals x squared minus x to the 4 plus 1. So I want to take this and I want to compute f of negative x. And that will require me to plug in negative x for every instance of x in the formula. And we want to simplify. So this was an exercise that we did in section 1. So if you need some review on how to substitute in, go back to section 1. And what we should get is x squared minus x to the 4 plus 1 after we simplify. And it's interesting because that equation kind of looks familiar, because that was something that we saw with the original equation that we were given for f of x. So in other words, I can say thus f of negative x is actually exactly the same as f of x. So my f of negative x computation ends up looking identical to the original function. And the definition for an even function says that this condition would have to be met. So we've just shown that. So therefore, f is an even function. And that's all there is to that proof. Let's try this for part B. Part B, we have a function called g, and g of x is x cubed plus x. So again, I want to do a computation. This time it's going to be g of negative x, and with this computation I'm going to take negative x, raise it to the third, plus negative x, and I want to simplify as much as I can. So g of negative x is going to become negative 1 times x to the third minus x. And I have to admit, that does not look exactly like the original equation. However, it does look like it's the exact opposite of the original equation. And that's what the definition for the odd function is looking for. Is your g of negative x exactly the opposite of the original function? And it is. So we can see that this x cubed is positive, but down here it's negative. Here I have plus x, and then here I have a subtraction of x. They're exactly opposite. So when they're exactly the opposite, I can say this. Thus, g of negative x is equal to the opposite of g of x. And we say the opposite of g of x by saying negative g of x, or negative 1 times g of x. So therefore, g is an odd function. And let's do this for the last one. Let's take a look at C. Let's compute h of negative x. This is going to be negative x squared plus negative x. And we will simplify like we did on the others, positive x squared minus x. And just like on the other examples, I want to compare this to the original equation given in my function definition. And there's a couple of conclusions that I can make. Well, for starters, what we just wrote, h of negative x, does not look identical to h of x. And it also doesn't look the opposite of h of x either. So h of negative x is not negative h of x. So this is a process of elimination. If it's not even, which is what this is saying, this is implying not even. This is saying not odd. And if I can conclude that it's not even nor odd, then there's my answer. So h is neither an even nor an odd function. And this is what many of the functions will be like. It takes a special type of function to be able to be an even or an odd function. So the majority of functions that we work with typically aren't either even nor odd, but I wanted you to be able to see what it looks like to compute and prove each one of these types of function.